My name is Duncan Watts. I'm the co-chair of the program committee, along with Michael Kearns, for Collective Intelligence 2014. I just want to welcome you here today. Thank you all for coming. We've got a wonderful program. We have about 227, as of yesterday, 227 registered attendees, which is a great attendance for a conference that's only been run for the second time. We have a wonderful lineup of talks. We have 20 invited speakers from many different disciplines, and you'll be hearing them over the next 2 days. We also have a great submitted program this year with 18 talks in 2 sessions of 3 tracks each. And we have 2 very large and vibrant poster sessions occurring over the next 2 days with a total of 105 posters. So many of you will be presenting in one form or another, and that's exactly the kind of interactive experience that we were hoping to create. Before I say more about the topics, I just want to point out the obvious in-your-face hashtag over here that Liz Gerber, the communications chair, has emphasized repeatedly that I should mention to you. If you are into social media or Twitter or anything and you want to talk about the conference, please do so using the hashtag CI2014, and that will be great. Let's see. So just to say a little bit about the content of the conference, we do have a really exceptional range of speakers over the next several sessions. We're going to be hearing everything about collective decisions in fish, insects, human, and robots this morning, and then moving on to collective cognition at the neuronal, the individual, and the group scales. We'll hear about collective governance in democracies and crowds, and collective problem solving in contexts ranging from the Cuban Missile Crisis to translation to crowdsourcing in disasters. There's going to be many other topics as well, both between the invited and the submitted program, spawning the gamut of collective intelligence in information, biological, and social sciences. This is exactly what we're hoping to stimulate here. In addition, we have 2 quite special sessions that we've created this year. The first one will be happening this afternoon and was put together by Scott Page. This session is going to be on the topic of the IARPA prediction contest. And so we'll have a representative, Jason Matheny, from IARPA, and a number of participants in this contest to talk about their experiences and what worked and what didn't work. And then tomorrow, Beth Novak will be hosting a very special Ignite session that she calls Geeks Meet Wonks. So you decide which team you're on. So this is going to be a series of short presentations by public interest wonks looking for researchers to help them meet crowd intelligence challenges. So the idea is people with problems, people with applied problems in the public interest sphere coming to talk about those problems to researchers who may or may not be able to help. And then, of course, we have our 2 great poster sessions happening today and tomorrow at lunchtime. Before I start the first session, I want to say a few words of thanks, first to our sponsors, the National Science Foundation and Microsoft Research. I want to give a very special thanks to our general chairs, Jeff Nickerson and Tom Malone, also to Liz Gerber, our communications chair, the local arrangements chairs, Sedia Ertekin and Lawrence Abel, the proceedings chairs, Jeff Bingham and Walter Lazecki. To all the program committee members, thank you so much for your efforts. Michael Kearns, Lada Adamic, Chris Chabris, Ian Cousin, Winter Mason, Beth Novak, Scott Page, Paul Resnick, Matt Selganic, Rajiv Sethi, and Anita Woolley. And finally, I want to thank all of you for coming. So I'm really looking forward to the next 2 days, and I'm sure it's going to be a great conference. So let's just get started with the first session. We're going to start with insects this morning, and we're going to have Stephen Pratt, who's Associate Professor at Arizona State University School of Life Sciences. He studies the emergence of complex social behavior in leaderless and decentralized groups, particularly social insect colonies. So I want to welcome Stephen. And I'll just say very quickly, the speakers this morning and in the other plenary sessions will be speaking for 20 minutes each. We'll be doing a quick turnaround in between the speakers and I'll just introduce them in turn. And please save your questions, except for perhaps just very immediate questions of clarification. Save all your questions to the end, and we'll have a 25-minute panel session where everyone will be able to do Q&A. So thank you for doing that.
All right. Thanks very much, Duncan. Thanks to you and to the other organizers for the invitation to come to this meeting. I think it's going to be really exciting. I think we're sort of moving up the phylogenetic tree this morning, so we start with insects, which maybe is appropriate. I mean, social insects that I study are maybe a canonical example of decentralized decision-making or collective decision-making. Colonies can, build complex nests, decide where to live, what to eat, organize collective defense. And they do this all in a highly decentralized way without any kind of well-informed central leader. So they really are kind of an extreme case of collective decision-making when they carry out some cognitive task. And so one of the nice things about, in addition to the fact that they're such a great example of this phenomenon, another nice thing about them is that they're relatively easy to experimentally dissect. And this is because compared, say, to one of the things that are often compared to a brain, in the same way that cognition emerges from interactions from a large number of neurons in a generally similar way, cognition in a colony emerges from interactions from a large number of ants, say, in an ant colony. But there are fewer ants, and they're less well integrated. And it is therefore easier to sort of specify the contribution that each individually identified ant makes to some collective task, like making a collective choice of where to live. So these are the ants I work on. It's a genus called Temnothorax. I've individually marked them here with pink drops. And so what I want to talk about today is kind of two aspects of this kind of study. The first one is taking advantage of this very tractable system to break down some collective action, like making a collective choice of where to live, into the specific behavioral algorithms that control the behavior of each of these ants. And it allows them interacting in a leaderless way to produce a very functional, coordinated group outcome. But the other thing I want to do is sort of take advantage of the way that this can be pulled apart to compare what a colony as a whole can do with what an individual ant can do, to sort of see what is gained or perhaps what is lost by combining large numbers of brains into a single collective brain. So the particular task that the ants carry out that we're most interested in is decision-making about where to live. So these ants normally live in naturally occurring cavities like hollow nuts or a rock crevice. You can open up this crevice, and there's a colony of these ants living inside. It's a very fragile kind of home. They frequently have to move. And when they move, they have a fairly challenging decision ahead of them. They have to maintain consensus, so move the colony as a cohesive group. But they also have to consider a number of possible cavities out there in the forest floor, some of which are better than others. And ideally, they'll reach consensus on the best one in a relatively short period of time. So that's a challenging task. It's one we study in the lab. We move them into an artificial cavity like this little wood and glass nest. It's sort of a rough mimic of the ones they live in nature. And we pose them problems at a smaller scale than they normally work in, but not that much smaller. They're very small ants. They're only about 3 millimeters long. And we give them a nest. We put them in a nest. We destroy that nest. And then we give them a choice between some pair or larger number of alternative sites that may vary in design. And by doing this many times, we learn that they have quite specific preferences among different kinds of cavities according to different physical features, like the size of the cavity, the size of the nest entrance, the darkness of the cavity. These nests are getting worse as we go from left to right. This is the best one with a tiny, easily defended entrance and a large cavity, and this thing is barely shelter at all. And they're quite effective as a group at choosing the best one. So in other words, if we force the colony to move, we'll find a few hours later that they have, with high reliability, moved into the better of a pair of choices, say. And they do this, as I say, in a highly decentralized way. There's no well-informed ant that's collecting information and knows which is the best nest. They do it, as social insects in general do, they do it very locally by an individual ant sharing a bit of local information she has with a limited number of her nestmates. So the way they do it, you've probably heard of ants laying chemical trails to lead other ants to a say, a nice food source. What these guys do, they don't do that. They instead, this ant, say, has found a good nest, and she is leading what's called a tandem run. So she's going to bring just a single nestmate to the site she's found. So this leader ant has found this nest, assessed it, and she thinks it's good enough to be worth at least sharing the information with one or a few of her nestmates. This ant will eventually make it there to that cavity, we hope, and she'll make her own independent assessment. And she may, too, decide to recruit like this. And they do this for a while until they've reached a quorum of ants at that new site. And if and when they reach that quorum, then the ants who have been leading these tandem runs will switch over to a more rapid form of recruitment, in which instead of painstakingly leading a single fellow scout ant to assess the site, they start to execute as fast as they can, which isn't really all that fast, but you'll see, as fast as they can, the move of their colony to the site. So this ant here is going to pick up one of her nestmates after a few seconds, and she'll carry her to the site. And she'll keep doing that again and again and again. So if you look at the overall pattern, what you see is an early phase of a small number of these tandem runs in which specialized scouts who assess nests and share information locally with each other sort of deliberate among sites, and then this execution phase in which the colony is carried fairly rapidly to one of the sites, the first site that reaches that quorum. So if we break down this behavior of individuals, of these scouts, into a kind of simple algorithm, it goes like this. An individual ant first decides that we need a new nest, maybe because I've destroyed their old nest. They find a candidate site and they assess it. And then they assess the quality of that site. Depending on how good they think it is, they'll start recruiting with some probability that is proportional to the quality of the site. And then they have to make a decision to canvass their fellow scouts by leading tandem runs. But if this quorum has been met, they instead fully commit to the site and they start these rapid transports. So there's more to be said about what they do than that, but I think that's enough to sort of give you a flavor of the kinds of sort of way they combine local information, a direct assessment of a site, with social information in the form of a quorum, in which they're paying attention to how many of their fellow nestmates are also attending to and visiting a given candidate. Now, when you think about combining lots of these individual insects and their own limited local information into a kind of aggregate, then this ought to make you think about this sort of classic wisdom of the crowds kind of thing, as exemplified nicely by the famous Francis Galton case of fairgoers in England judging the weight of an ox, and the average of their rather noisy guesses being a remarkably good approximation of the actual weight of the ox. So that's one thing one way to look at what these insects are doing. You can think of what we're looking at here as a sort of exploitation of wisdom of the crowds by combining many poor estimates into one good collective estimate. But the other thing that we can see, of course, with collective decision-making is sort of the opposite of this, where we see, the whole thing is relying heavily on positive feedback, right? Each one of those recruitment events unleashes another recruitment event with some probability. And essentially, it's a positive feedback cascade that is creating the quorum that triggers the commitment to a site. But of course, positive feedback cascades have their downside. I was glad to see that later in this talk, there's going to be in this meeting, there's going to be talk about the Cuban Missile Crisis, which is a classic example of groupthink, of sort of excessive reliance on social information and a lack of independence in the decision-making of the members of the group. I think the consequences are less dire when ants fall into groupthink, at least from our point of view. From theirs, it can be very bad indeed, though, if a colony, for example, finds itself, perhaps due to early errors by a few scouts, finding themselves pulled by an information cascade into a poor nest. And the consequences can be rather dire because they need these nests to defend themselves and to create an appropriate microenvironment for the growth of their brood. So a poor decision can be costly. So when we ask about what these scenarios are about, or what happens when you combine many brains into a single collective, you get a sort of an enhancement of cognition, or maybe in some cases a diminution. So we wanted to treat this experimentally by comparing, by basically challenging colonies in the way I've described with some decision task, whole colonies, but also taking individual ants out of a colony and challenging them with the same task, and then seeing what changes or differences, if any, in performance we see between the individual level and the group level. So I've showed you how we can challenge a colony. Basically, we give them some nests, and we destroy their nests, and we see what the colony does, where they move to. We can do something similar with a single ant. We take a single ant out of the colony, which is I admit, a very unnatural thing to do. Ants are highly social animals. But we can manipulate them in this experimental way, put them in a little dish like this, put them maybe with a couple of brood items, the young larvae that they treasure very highly, in this nest, destroy that nest, and give them a choice of 2 new nests, and then see over time which of those 2 nests the ant chooses to move those brood items into. It's like a miniature version of the colony emigration that I showed you earlier. And the ants will do surprisingly well at this. And we've used this method. We've given them a lot of different kinds of tasks and compared individual and group performance. I'm just going to talk about one of them here. This is basically ant psychophysics. So what we do is kind of give them, and I can ask you which of these 2 squares is darker, and hopefully you'll find that an easy question to answer. And then I can make it a little harder, and a little harder, and a little harder, and a little harder still. And I can keep making the discrimination task here more and more difficult. And this is a sort of a classic way to look at how brains deal with physical stimuli. And so what we can ask here is what's the smallest differences that you can discriminate? So the way this thing is working, right, is in every case, the left square is darker. I'm not changing it at all. I'm just changing the comparison one. And so I can basically do an experiment like this in which I offer a subject a series of choices of varying difficulty along these lines. And I choose darkness here to show to you because it's easy to see, but also because that's what we do for the ants as well. So ants, it turns out, the single nest attribute that they most care about is darkness. So they will always prefer a darker to a brighter nest. And that's probably because it's an indirect indicator of nest wall integrity. And a wall with holes in it is going to let light in. A wall without holes will be very dark. So if you give them a choice between a darker and a brighter nest, otherwise identical, they'll always pick the darker one, if they can tell that it's darker, right? So what we do is we give them a series of choices where we have a constant, very dark nest, and then a comparison nest that varies in brightness. And so we can have difficult choices over here on the left, where the comparison nest is only a tiny bit brighter, and easy choices over here, where the comparison nest is much brighter. And then we can plot a function here. We get a lot of data on this, offer for each of these comparisons many, many choices. It's a difficult experiment to do. It requires many, many of these experiments in which we face either a colony or individual with these choices. And we can take that data, which I'm not showing you yet, but I will in a second, and we can fit some function to it. This is a useful one. Very often, these psychophysical functions have this kind of step-like form. This is one example that we've been using to fit this data. And what's nice about this function is it has a couple of readily interpretable parameters. One of them is alpha here, which we can say is the sort of brightness difference at which the subject shows a 50% probability of getting the right answer. Another thing we can look, and we can call that the detection point. The other one is lambda, which indicates where their performance saturates. In this case, it's some difference they can get right 100% of the time, but that isn't always the case. So if we take individual ants and we subject them to this kind of experiments, then we see a pattern like this. And this is a fairly typical kind of psychophysical function in that it starts poor here with a very difficult one, or a literally identical one. They just perform at chance. And then they get slowly better, and they have this step-like increase in performance, and then it plateaus. So that's reassuring that we see a sort of normal-looking function that gives us some confidence that pulling an ant out of a colony hasn't been too unnatural a thing to do. They're still behaving in a kind of rational way. When we give the same choices to colonies, we see something like this. So first, we see much better performance at the more difficult end of the spectrum, right? So for these very small differences, colonies do much better than individuals do. Sort of a wisdom of the crowds kind of effect, right? In some sense, combining all these noisy measurements, individual noisy measurements of the brightness, combining many of them is leading to a kind of averaging effect, perhaps in the same way we see with Galton's ox. But then if we keep going and making the choice easier, then for the very easy ones, then we get a reversal of this. It's not a very large reversal, but it is a consistent, and it's a real reversal. In other words, if the choice is really easy, the colonies do worse than the individuals. We see not an enhancement of performance by combining many noisy estimates, but a slight reduction of it. So there's a couple of ways of thinking of this. We can think sort of generally, in one sense, in some parts of this problem space, combining many estimates is helping, but in other ones it's not. So what we wanted to do is link this more to what we learned about individual behavior. So again, we return to the observations we've made about the kind of behavioral algorithms, the behavioral rules that the individual ants use in the course of making a decision. And we produced this kind of simplified model of what we think is going on here. And the idea here was mainly to represent the two key aspects of an individual's decision making. As I mentioned before, she's basically combining her direct personal information of a nest she has seen with social information in the form of a quorum rule. So let's say, for example, we talk about an ant who's evaluating a good nest. She's visited that good nest. That's the only nest she's seen. And so she's combining personal information, which is just what we just represent here is this probability of choosing that nest based on its quality, plus this social information in the form of a quorum. In other words, the more of her nestmates are there in this step-like way, we'll see an increase in her probability of making a decision, of making a commitment to that site. So we can imagine ants, the way to think about this model is individual ants are kind of bouncing around. They're visiting one nest and they're visiting the other. And every time they visit a nest, with some probability, they commit to that nest. They decide, this is going to be the one, let's move to it. Or let's start transporting it, let's bring the brood to it. If we look at what's going on in a mediocre nest, it's the same idea. It's slightly more complex, but only because we're incorporating here, in addition to the ant evaluating the quality of the nest on its own merits, and in addition to paying attention to how many nestmates are there, the social information, she's also comparing it to her recollection of the other site, if she's seen the other site. So the idea here is that individual ants, they're not acting strictly in this extremely simple way, where all they do is look at the nest that's in front of them and count the ants that are near them and make a decision based on that. They do have a little bit of memory. And we have data that supports this. They remember, if they've already seen the good nest and then they visit the mediocre nest, they remember that. And we model the effect of that as being a gradual reduction in their probability of committing to that mediocre nest, depending on how many times they've seen the better nest. So the two things that are going on here, one is a very gradual individual process of comparison of the two sites, plus this quorum-based social information effect. And if we run this model on the, with reasonably realistic parameters we derive from data, then we see something similar, at least qualitatively similar, to the pattern we saw with the real ants. That is, we see this reversal where the colony is doing better. It's more likely to end up committing to the better site when the decision is hard, and less likely to commit to the better site when the decision is easy. And the way we interpret this is that essentially, for a hard decision, that individual comparative effect, the personal information effect, is very weak. It takes a really long time for that process to actually lead to a discrimination of these two probabilities that are initially very similar because the nest qualities are very similar. So in that case, the kind of amplification of small random differences that you get from the quorum rule can actually help the colony more likely choose the better nest. But if you get to a very easy case, well, then the personal comparison is quite effective. And the only thing, and it will move quite steadily after a few comparisons to a high likelihood of the individual choosing the better nest. But the problem is if you have also the social information effect, which all you're really adding there is you're not really enhancing the likelihood of choosing the better nest anymore. You're just throwing in the possibility of occasional information cascades in which, just by chance, you reach a quorum at the worst nest and you direct the colony to the inferior nest. So in other words, the contribution of this, the social information depends very much, whether it's actually going to enhance cognition, to use collective cognition rather than individual cognition, depends very much on the nature and the difficulty of the problem. So let me just conclude with this a little metaphor. I've basically been talking about comparing basically individual ants to members of society. But the other, as I mentioned at the top, the kind of metaphor maybe that I find a little bit more compelling is to compare an ant to a neuron, and to think of the collective cognition we're seeing as something that emerges in a kind of roughly analogous way. And our sort of general goal is to evaluate how that works and mechanistically and functionally what it actually contributes to the colony's life. So let me just quickly acknowledge a few people. The nice thing about having a lab is that you can take other people's work and present it as your own. So the work I've been talking here mainly, the last part especially, is the work of my student Takao Sasaki. A lot of other people helped on this, especially early on in uncovering these mechanisms. And I want to thank you all for listening.